Hello children, welcome back to the chemistry session. In previous session we have seen unit cell dimensions or density of the unit cell. In today's session we are going to talk about imperfections in solids. Imperfections in solids. Let us start today's session, children. We have discussed in earlier videos that crystalline solids exist in crystal lattice, and crystal lattice has made up of number of lattice points or lattice sites. If we see any crystal, the crystal is made up of number of crystal lattice, and they exist in different structures like primitive unit cell and body-centered cubic unit cell, face-centered cubic unit cell, and end-centered unit cells. We have seen these types of unit cell in earlier session. In this video, we are talking about imperfections or defects in solids. How can you say that crystalline solids have defects in them? Because during crystallization process, we might have observed some defects are identified in them. Those defects are due to arrangement of constituent particles in the solids. So these called imperfections in solids. These are broadly classified into two categories. One is point defects and line defects. What is meant by point defects? Point defects means these are irregularities or deviations from ideal arrangement of crystalline solids. This is due to these defects around a point or around an atom in a crystal lattice. This is called point defect. So point defect are the defects which causes due to the irregularities or deviations from ideal arrangement around a point in a crystal lattice. This is called point defect. Next, line defect. Line defect means these deviations from ideal arrangement when lattice points are arranged in the row. When we observe deviations, when the lattice points or lattice sites arranged in the rows of lattice points, this causes lattice line defect. In this class, we will confine our discussion to point defects. So let us see point defect, children. I have already given the definition of point defects. Point defects causes deviations or irregularities from ideal arrangement of the crystal lattice around a point or around the lattice site in the crystal lattice is called as point defect. This point defect is broadly classified into three types. They are stoichiometric defect, next one impurity defect, and the third one non-stoichiometric defect. These point defects are broadly classified into three types, and they are stoichiometric defect, impurity defect, and non-stoichiometric defect. So let us talk about stoichiometric defect. What is meant by stoichiometric defect? The stoichiometric defect, this kind of defect doesn't disturb the stoichiometry of the crystalline solids. What do you mean by stoichiometry? Stoichiometry means number of ions or number of atoms, fixed number of atoms present in the lattice points or lattice sites is called as stoichiometry. Stoichiometric defect doesn't disturb the stoichiometry of the crystalline solids. This stoichiometric defect again classified into two types. They are vacancy defect. vacancy defect, and next one interstitial defect. This stoichiometric defect again classified into vacancy defect and interstitial defect. Let us talk about vacancy defect. What is meant by vacancy defect? We have already discussed the definition of point defect, which causes due to deviations or irregularities from ideal arrangement around a point in the crystal lattice or crystal site is called as point defect. So vacancy defect causes due to in a crystal lattice some of the lattice points or some of the lattice sites are vacant. This causes vacancy defect. Suppose it's a crystal lattice. We know that this crystal lattice made up of number of lattice points or lattice sites. If some of the lattice points are vacant in the crystal lattice, some of the lattice points are vacant in the crystal lattice, this causes vacancy defect. So this is one vacant site and this is another vacant site and this is third one. In this crystal lattice, some of the lattice points or lattice sites are vacant. This causes vacancy defect. And one more point, this vacancy defect decreases the density of the solids. This is because density of the solids depends on the number of lattice points or lattice sites present in the crystal lattice. When crystal lattice contains less number of lattice points, then it obviously decreases the density of the solid. That's why this vacancy defect decreases the density of the solid, and this defect arises on heating the solids. On heating the solids, then this vacancy defect arises. That means some of the lattice points are removed from the crystal lattice. It's called vacancy defect. Next, interstitial defect. Let us see what is meant by interstitial defect. Interstitial defect, it causes due to the some of the lattice points or lattice sites present at the interstitial positions of the crystalline solid. Let us see diagrammatic representation of interstitial defect. Let us consider it as a crystalline solid. Now we are arranging lattice points or lattice sites in the crystalline solid. This interstitial defect arises due to some of the lattice points or lattice sites present at interstitial positions or interstitial site like this. Earlier, this crystal has regular arrangement, but now some of the lattice points or extra points are present at the interstitial positions of the crystalline solid. This causes interstitial defect. This interstitial defect increases the density of the solid. I hope you understand, children. Vacancy defect, this is some of the lattice points are vacant in the crystalline solid, which causes vacancy defect. And interstitial defect means some of the extra lattice points are present at the are located at the interstitial site, which causes interstitial defect. This interstitial defect increases the density of the solids. Remember, children, this vacancy defect and interstitial defects do not disturb the stoichiometry of the crystalline solids. And only non-ionic solids possess this vacancy and interstitial defect, but not ionic solids, because ionic solids must possess electric neutrality. That means we know that ionic solids are made up of cations and anions. So number of cations or cation charge must be equal to the anionic charge. That's why electrical neutrality must be balanced in ionic solids. So ionic solids do not possess vacancy and interstitial defect. They possess Frankel defect and Schottky defect. Let us talk about them. Frenkel defect and Schottky defect. Let us see what is meant by Frenkel defect. We discussed earlier that this Frenkel defect as well as Schottky defect is possessed by ionic solids. We know that ionic solids are made up of ions, cations and anions. Let us see the diagram of ionic solid, which is made up of cation and anions. It is nothing but ionic solution which is made up of cations and anions. We know that cations are smaller in size and anions are larger in size. So Frenkel defect showed by ionic solid. So ionic solid shows Frenkel defect in such a way that the ions which is smaller in size, that means cations are dislocated. Cations are dislocated from its original position to new position. Suppose it is the first row chamber. Here there is a cation present here. Suppose this cation is dislocated from its original side to the new side. Somewhere this cation is present. So cation is dislocated from this side to this side. This is original side and this is new side. Now, during this dislocation, this causes vacancy defect at its original site because there is no ion present here. So, at original site, it causes vacancy defect, and at new site, it causes interstitial defect because here there is no ion present here, that's why it causes vacancy defect, and here extra ion is present here, so that it causes interstitial defect. So this is possible when ion, especially cation, because the cation has smaller in size, that's why the cation dislocated from its original site to the new site, then it causes vacancy defect at its original site and interstitial defect at new site. In general, ionic solids possess Frenkel defect. There is a large difference between the size of the ions, and there is a large difference between the size of the cations and anions. They possess Frenkel defect. The ionic solids like zinc sulfide and silver chloride and silver bromide and silver iodide. In general, these solids, these are examples of ionic solids. So they possess Frenkel defect because there is a difference between the size of the cations and anions. When there is a large difference between the size of the cations and anions, then those ionic solids possess Frenkel defect. And one more point, this Frenkel defect also called as dislocation defect. Which is also called as dislocation defect, because dislocation of ion from original side to new side. That's why Frenkel defect also called as dislocation defect. Next, Schottky defect. Next one, Schottky defect. This shortcut effect also called as simple vacancy defect. Simple vacancy defect. Remember children, both Frenkel defect and shortcut effect shown by ionic solid. Ionic solids possess both Frenkel defect and the shortcut defect. See, this shortcut effect also called as simple vacancy defect because we discussed earlier that ionic solids must contain electrical neutrality. That means the number of cations must be equal to the number of anions in a crystal lattice. That means the number of removal of cations is equal to the number of removal of anions, because we have already discussed vacancy defect. Vacancy defect means some of the lattice points are, some of the lattice sites are vacant. Then it causes vacancy defect. So in a crystalline solid, ionic solid, some of the lattice sites are vacant. So this crystal shows shortcut effect because the number of removal of cations must be equal to number of removal of anions. So in this crystal, 2 cations as well as 2 anions must be replaced, must be removed, because there are 4 vacant sites in the crystal. That means 4 vacant sites means 2 must be cations and another 2 must be anions. So this is called as simple vacancy defect, and which is most common defect in ionic solids. If you take any ionic solid like sodium chloride, potassium chloride, cesium chloride, they possess this kind of defect. So this is called as shortcut defect. And the ionic solids which possess shortcut defect, there must be a almost similar in size of the ions. That means the size of anion as well as cation must be almost similar in size. When there is a similar in size of the cations and anions, they possess shortcut effect. Examples. For example, sodium chloride, NaCl, potassium chloride, KCl, and cesium chloride, CaCl, and silver bromide. These solids possess shortcut effect. Sodium chloride, potassium chloride, cesium chloride, and silver bromide. These are ionic compounds. These solids possess shortcut effect. Remember, note point here, silver bromide possesses both Frenkel defect as well as shortcut effect. This is called stoichiometric defect, children. Stoichiometric defects do not disturb the stoichiometry of the crystalline solids. They are broadly classified into vacancy defect and interstitial defects. Vacancy defect causes due to when lattice points are vacant, it causes vacancy defect. Interstitial defect means when extra or additional lattice points or lattice sites present at interstitial positions, it causes interstitial defect. This is only limited to the, only applicable to the non-ionic solids. So ionic solids possess Frenkel defect and shortcut defect. Frenkel defect possesses ionic solids when there is a large difference between the size of the cation and anion, and this is also called as dislocation defect. That means dislocation of cation from one side to another side. This is called as Frenkel defect. And shortcut defect is also called as simple vacancy defect because removal of ions from the ionic solids. Here, number of removal of cations must be equal to the number of removal of anions. This is called as shortcut defect. Ionic solids possess shortcut defect when there is a almost size of the cations as well as anions. So this is today's section, children, imperfections in solids, and still we need to discuss impurity defect and non-stoichiometric defects. That we'll discuss in next session. I hope you understand today's session, children. We'll meet in next session. Thank you.